Welcome to my presentation in the Digital Materials Research and Development session. In this presentation, I will give you an overview about the latest and greatest features of Geodic 2023, specifically for digital materials R&D. I want to thank all the colleagues that have contributed to this presentation. But first, let me introduce myself. My name is Oliver Rimmel. I studied mechanical engineering at the University of Kaiserslautern with a focus on material science and composite materials. After this, I joined the Leibniz Institute for Composite Materials in Kaiserslautern as a scientific assistant in the Department of Manufacturing Science of Composite Materials. I concluded this work with a PhD in the field of experimental and simulative analysis of composite impregnation processes. After this, I worked at PFW Aerospace in Speyer in the field of additive manufacturing for titanium materials. In 2022, I joined Math2Market as a business manager for digital materials R&D. This field includes, but is not limited to, foams, composite materials, ceramics, metals, additive manufacturing, nonwovens, and technical textiles. In my talk today, I'm going to start with the introduction of a new Lear-based solver in Elastodict, which is great to estimate stiffness of structures, especially with symmetric boundary conditions and high porosity. After that, I will show a new workflow in FormGeo that makes it easier than ever to create a digital twin from 3D data using a new feature. Subsequently, we will have a look at improved meshing capabilities, facilitating the export of geometries from Geodic to other software. Then, you will see how FiberGeo was improved to help you recreate a digital twin from the fiber-find analysis of a given geometry. Last but not least, I will introduce you to a new Geo app, which is very useful to estimate the stiffness of one constituent material in a structure. Let's start with the new Lear-based solver in Elastodict. As you know, Elastodict has been using the FieldMash solver, which is developed by Fraunhofer ITWM. In Geodic 2023, we are introducing an additional solver. Very often, our customers are interested in the mechanical properties of highly porous structures such as nonwovens. From Flowdict, you might already know our Lear solver. It is valued by our customers for very memory-efficient implementation, relying on an adaptive grid with low memory usage, especially for highly porous structures. We use the same advantage now also for computation of the Young's modulus of a structure in Elastodict. From now on, you can choose the Lear solver in the Solver tab of the Effective Stiffness options. This is an example structure consisting of aluminium struts. The modulus of the constituent material is 69 gigapascals. In the tables on the right side, you see a comparison of runtime and computed modulus in 3 directions of the two solvers. The upper table is for periodic boundary conditions, while the lower one is for symmetric boundary conditions. In case of the periodic boundary condition, the Lear solver computes comparable values for the moduli of about 0.66 gigapascals for E1 and E2 and 0.21 gigapascals for E3. The runtime of FieldMath is 187 seconds, while Lear takes 112 seconds. This is already a bit faster, but no big difference. However, when it comes to symmetric boundary conditions, the Lear solver computes the stiffness in 77 seconds, compared to 1020 seconds of the FieldMath. In this example, we are looking at a glass fiber reinforced polymer with a fiber volume content of 11.3%. And as this is a composite material, there's very little to no porosity. Just as in the samples before, we compare runtimes of the two solvers and computed stiffnesses in 3 directions, for periodic and symmetric boundary conditions. For periodic boundary conditions, the FEMAR solver is quite a bit faster with 37 seconds versus 46 seconds. The Lear solver, however, is much faster with 37 seconds compared to 188 seconds for the symmetric case. The computed stiffness values are comparable in both cases. Yet, for an example like this, looking beyond Young's modulus to higher strain percentages and possibly damage is often required. As of now, only the FEMAR solver is capable to do this. When we come to highly porous materials, the situation changes. You might know this structure from previous presentations where we have shown analysis and recreation of in situ compression of this aluminium foam within a microcity. As mentioned before, this is a great example for the Lear solver, as the scan cannot be computed with periodic boundary conditions and there is a high porosity of over 95%. You can see that the Lear solver is able to compute the stiffness in 90 minutes, while the FEMAR solver takes more than 10 times longer, in this example 1234 seconds. In this case, also the memory usage of the Lear solver of just 2 GB compared to 10 GB that the FEMAR solver needs shows its high efficiency. Comparable to what made the Lear solver great for flow calculation, the big advantage here is the adaptive grid. As you can see in the images on the right, with a regular grid, the grid has to be sufficiently fine to resolve all peaks in strain or stress. Needing a finer grid in some areas means that all areas need to have a finer resolution. With the adaptive grid, it can be refined just where needed. Furthermore, in case of the highly porous structure, the pore space doesn't need memory or computing efforts. It means in this case that 95% of the whole domain can be neglected in computation. To sum this up for you and give you a hint on when to use which solver, here is a brief comparison of the two solvers. The FEMAR solver is great when it comes to computation of not only stiffness, but also large deformations or flexural tests. It is very good for solving with periodic boundary conditions and anisotropic and nonlinear material laws. Geometric nonlinearities can be taken into account. A standard example is a fiber reinforced composite material with low to no porosity, where you would like to look beyond the linear elastic behavior. In the graph shown, you can see an example of a composite incorporating a damage model. The Lear solver is introduced with GeoDict 2023 for effective stiffness calculations, especially but not only for symmetric boundary conditions. It is very fast and memory efficient, especially for highly porous structures. The graph shows the stiffness of the structures in a polar plot in several planes. Stay tuned for more features that will come in the future to expand applicability of this great technology. After having a look at solvers for mechanical properties, let's take a step back and talk about structure generation. With GeoDict 2023, we are introducing a new feature for FormGeo to help you recreate your foam as a digital twin in GeoDict. Up to GeoDict 2022, building a digital twin of a foam imported from a microcity meant some manual work. Very often, the workflow involved running GrainFind on the pore space to compute the metrology of the foam. In the next step, the grains were recreated in GrainGeo. With the recreated grains, it was then possible to run FormGeo and have it recreate the struts around the grains that represented the pores inside the foam. In total, this meant the user had to conduct quite a few steps. In GeoDict 2023, this has become a lot easier and more streamlined. After running Identify Pores in GrainFind, you can just use the new button in FormGeo. GeoDict sets up everything for you to recreate this foam and have a starting point for your study. In the next steps, you can start to change parameters and use the created models to compute the properties that are useful for you. This could be, for example, electrical or thermal conductivity, mechanical properties, or even acoustic absorption. The example shown on the left is a microcity of a random form after segmentation. In the image in the middle, you see the result of pore identification run in Porodict. With this result, FOAMGeo was used to create a digital twin. In the next few slides, let's have a look at the improved meshing capabilities in Geodict 2023. Our solvers integrated in Geodict provide you with fast and accurate results for a wide range of applications. But of course, there are also workflows that involve exporting geometries generated in Geodict to a mesh. This mesh can subsequently be imported into other tools such as ANSYS and COMSOL for further computations. In Geodict 2023, these capabilities have been improved to provide meshes with higher quality. Edge length can be predefined by the user to adapt to the specific need of mesh refinement. Triangle aspect ratios are improved to provide high-quality meshing. Furthermore, remeshing has been improved in speed. In this example, you see a sphere represented in voxels on the upper right. Below it, there is the original mesh created from this voxel structure. The other images showed the sphere after remeshing with different edge lengths. You can see that represented structure is a lot smoother and closer to a sphere. On this slide, you can see two examples of structures generated in Geodict that have been meshed using MeshGeo. The upper example shows a fibrous structure, while the lower structure shows a cutout similar to the foam that you have seen in the FOAMGeo section of this presentation. Depending on what you would like to compute on such a geometry in other software, and the size of geometrical features, the fineness of the mesh has to be adapted. In these examples, you can see the original mesh derived from the voxel structure on the left side. Next to them, you can see different results of the new remeshing algorithm with different presets of edge length, where you can adjust between the level of detail and number of triangles of the mesh. In the previous slide, we have seen an example of a fibrous structure. In the coming slides, I will show you a very useful enhancement in FiberGeo that helps you to build a digital twin of your fiber structure. When starting from a micro-CT scan, using FiberFind AI is a great way to find the single fibers within the structure and to compute statistics on them, such as diameter distribution, length distribution, orientation, curliness, or curvature. To create a digital twin of that, our FiberGeo is a great tool. Up to Geodict 2022, you could generate a fiber structure, let FiberFind AI run on that, and compare the statistics mentioned before with the statistics on the original structure. Depending on the geometry, it takes some loops until they fit well enough. In Geodict 2023, we made it easier for you. When creating a fiber structure with FiberGeo, it now displays the same statistics that you could previously obtain with FiberFind AI out of the box in the result of a FiberGeo creation process. This makes it a lot easier and faster for you to get to your digital twin. This also enables a way of optimizing the FiberGeo creation parameters automatically within a Geo app. If you are not yet familiar with the concept of Geo apps, stay tuned for the presentation by my colleague Matthias Fingerle later in this session. Speaking of Geo apps, here is one that we would like to present to you. Composite materials possess a complex material behavior as the properties of several constituent materials influence the behavior of the composite. Very often, not all properties of all constituent materials are known. For example, the Young's modulus of fibers can be derived from datasheets or single fiber measurements, while the Young's modulus of the surrounding polymer is unknown, or vice versa. Geodict 2023 contains a GeoApp with the name Stiffness Estimation that lets Geodict help you determine the stiffness of a constituent material. This app can be found in ElastoDict GeoApps. For this, you need a geometry model of a representative volume element and the stiffness of the composite. After entering this into the GeoApp, Geodict will fit the unknown stiffness of one material ID to the properties of the entered structure. In further steps, we will expand this feature to also allow you to fit plasticity and damage parameters of a material to reverse engineer constituent material properties from a measurement of a composite material. To sum this up for you, here are the most important points of my presentation. With Geodict 2023 you can use the new Lear solver to compute stiffness very fast for porous structures and or symmetric boundary conditions. Generate forms easily by importing an Identify Pores result in FormGeo. Create better meshes using the new remeshing. See the analytics from FiberFind AI directly in FiberGeo when creating structures. Estimate the stiffness of one constituent material from the composite stiffness and the geometry. Thank you very much for your attention. I'm looking forward to answering your questions. Stay tuned for a presentation by Nicola Henkelmann from Fraunhofer ITWM about fatigue damage prediction with Geodict, and a presentation by Tim Schmidt from Leibniz Institut für Verbundwerkstoffe about machine learning for permeability determination of fiber structures. The session will be concluded by a talk by Matthias Fingerle about GeoApps and Math to Market consulting and project services. After the break, we hope to see you in one of our workshops, where you can try out Geodict 2023 yourself on one of our virtual machines with examples presented by my colleagues.